will tell us about monopoles, scattering, and generalized symmetries.
Thank you. Okay, thank you very much for the invitation. It's a big honor. It's a pleasure to be here. Thank you for coming. Indeed, I'm going to tell about a paper that came out during the summer. Here's the archive number. It's a paper written in collaboration with Marieke van Beek and Zohar Komarkovsky at Stony Brook, together with Philip Boyle-Smith, who's in Tokyo right now, and David Tong, who's at Cambridge. At that time, I might mention some work in progress with these people, together with Rishi Mulan, who's also at Cambridge. I have to say that I changed my mind last minute and I decided to do Blackboard instead of slides. Hopefully that makes it a little bit more dynamical, but I didn't have time to write everything here. So at the end, I might improvise a little bit or maybe check my computer to see that I may say everything I wanted to say. Okay, so the basic idea is very, very simple. What we're going to do is we're going to take a very heavy monopole here. We're going to throw in some leptons here, electrons, for example, or whatever. And then we're going to place a screen. And then we're going to measure what comes out here. And the question is, what is the screen going to measure? Okay, so this is a very simple problem, but it turns out that it has some funny features. Okay, so let me begin with a very quick review of some background. Mostly so that we are all using the same notations. I won't go into details because they were not important. But of course, if there are any questions that you want me to elaborate, I'll be happy to. Okay, so let's begin with a four-dimensional theory of fermions, plus perhaps other stuff. And let's assume that there is a flavor symmetry, which is the U1 flavor symmetry, generated by some current J mu. Okay, so it's a very old, well-known fact that if you compute the three-point function of J, this is given by like a sum of Feynman diagrams of a form like this, with fermions running through the loop, and you put a current on each vertex. And in general, this is non-zero. So that means that the current is not conserved, strictly speaking, or the conservation is a little bit weird. And because we call this an Etoft anomaly, when we say that the symmetry is anomalous. Okay, and more generally, you can have any symmetry G generated by some currents, and you may have the same phenomenon where the current is not strictly conserved. It's a little bit fishy whether it's conserved or not. And when this happens, this is actually a good thing because it gives you lots of interesting constraints on the dynamics of your theory. So for example, there's one simple constraint, which is that if the current is conserved, that means that G can be gauged. Of course, if the current is not conserved, you cannot couple it to gauge fields because gauge fields require the current to be conserved for gauge invariance. But there are other facts that you can say that they are equivalent. So for example, when the symmetry is non-anomalous, that means that there exists a G-symmetric deformation. So the empty theory. So when you have an anomalous symmetry, that means that there is no symmetric deformation that takes you to that theory, to the trivial theory. There are more constraints. For example, there exists as G-symmetric.
What is the converse of this?
Well, I mean, okay, for a U1 symmetry with a continuous symmetry with perturbation, for discrete symmetries, it's very subtle whether the two are equivalent. If you have an anomaly, that means there is no deformation. If you don't have an anomaly, it's strongly believed that there is a deformation, although it's not proven.
That's using the word deformation somewhat liberally.
Yes. So by that, I mean any smooth change that you can make flowing up or down, stuff, whatever you want. Yeah. Yes, there are lots of subtleties here that I'm going to be skipping. Right, thank you. The anomaly also tells you whether there's a G-symmetric lattice realization of the theory. If you have anomalous symmetries, it's a very old story whether you can put that on a lattice in a way that preserves symmetries, in a way that acts on site and in a nice way. There are more constraints. For example, if you have an anomaly, that also tells you whether there is a G-symmetric boundary condition. Etc. So anomalous symmetries give you lots of constraints on what you can do to your theory in a way that is compatible with G-symmetry. And I'm oversimplifying here. For the boundary condition, you want to impose like some nice constraints that you want, like a unitary boundary condition, that's simple, blah, blah, blah. Anyway, the basic idea is that anomalies give you constraints of this type. Okay, there's even more constraints if you have like a product structure, because in that case you can put different currents inside the correlation function. Instead of putting the same current 3 times, you can put a current for one group and a current for a different group. So for example, if you have a U1 1 times U1 2 symmetry, then you can do correlation function like this: J1, 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 J2, J1, J2, 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 right? So the first and the last are the same anomalies as before. These tell you whether U1 and U2 can be gauged separately or not. But let's, for example, assume that this is 0. So this is 0, so that means that U1 can be gauged. So let's actually go ahead and gauge it, and then we ask what happens to the other symmetry once you gauge the first one. And these two anomalies here will determine the fate of the second symmetry once you gauge the first one. Okay. So for example, when this one is non-zero, that tells you that U1 2 becomes non-invertible. When this one is non-zero, that tells you that U1 2 becomes a 2. Okay, so this is some phenomena that has been discussed very recently in the literature of what happens to a symmetry when you gauge a different symmetry such that the two have mixed anomalies. Okay, and okay, let me see. So what do I mean by this? For example, by non-invertible, what I mean is that that's a symmetry. That's something that commutes with the Hamiltonian, but it doesn't have an inverse. You cannot undo the symmetry. So for example, in this example, U1 non-invertible, it still acts invertibly on the fermion, so its psi goes into the I of psi. Of course, that's invertible because you can just rotate by the opposite phase and that undoes the transformation, but it's non-invertible on a dot line. So if you have a dot line and you apply the transformation, what you get is basically a dot line dressed by a Wilson line. Okay? And this is basically the Whitney effect in action, because when you do an axial transformation, that generates a theta term, and the theta term by the Whitney effect gives electric charge to the dot line. Okay? And this is a non-invertible operation because you cannot undo it just by doing some other transformation. There's also another explanation of this fact, which might be more familiar to people that are more condensed matter people. So another way to understand why this symmetry is non-invertible when you have that type of anomaly is that because you want to undo the anomaly in some way, and the way you do that is by stacking with 3D TQFT. So when you perform the rephasing of the fermion, at the same time you want to stack on top with a 3-dimensional TQFT that is engineered so that the anomaly cancels. Okay, this is what condensed matter people call the Hall effect, Hall state, which by definition is just the boundary value. So this is, if you have like whatever, in 4D, this is total derivative. So if you have a boundary, it becomes a 3-dimensional object, which is called the Hall state. And it's basically data replacing because this is just the theta term, so it's the same phenomenon as before. And by two group, what I mean by two group is that the U1, when I gauge the U1 symmetry.
Sorry, just to clarify, the whole U1 becomes non-invertible or just a subgroup of it?
It's kind of the other way around. There are some subgroups that are invertible, but in general, the whole thing is non-invertible. So for generic angles, it's non-invertible. For some special angles, might become invertible. Yeah. I'm oversimplifying a little bit. There's some issues as to whether you can rotate by an arbitrary angle or can only be rational.
That's what I was asking.
Yes. So for rational angles, it's non-invertible. For irrational angles, it's not clear whether the transformation is well defined at all or not.
Okay.
But the people will usually say in that case is by irrational angle, you just take the the defect to become like the zero defect. It kills everything, you could say, if you want. I mean, it depends on definitions, but
The
yeah.
statement is U1 to become non-invertible.
Well, for rational angles, it's non-invertible. For irrational angles, you can do more or less what you want. You can say that it's not defined for rational angles, and so it's not really a U1 symmetry, it's like a Q mod Z symmetry. Or you can say that it is well defined, but it's the zero defect. It's sort of whatever you prefer. Okay. And by two group, here what I mean is that the U1 zero form symmetry becomes entangled with a U1 one form symmetry. So when we gauge a U1 symmetry in 4 dimensions, there is an emergent dual one form symmetry. And when you have an anomaly of that type, the zero form and the one form, the new one form, become part of a higher categorical structure, which is called a two-group interlineation. Okay, and that gives some constraints beyond what we usually, like the usual constraints from symmetries. There's even more stuff when you have a two-group of this form. For example, you can argue that such symmetry is always emergent. It can never be an exact symmetry. Whenever you go to the UV completion of this theory, it necessarily has to be broken. So that means any UV completion will have some massive stuff that break the symmetry. There's also constraints on low energy phenomena. So for example, if you have some material that is described by this type of symmetry, then if you cool it down, for example, you can argue that if there is a superfluid phase transition, for example, it always has to happen before a superconducting phase transition. You cannot have the superconductor before the superfluid. So there are some constraints on what can happen or cannot happen to symmetries whenever you have these sort of structures. Okay, so this is all the background that I wanted to mention. It's just so that we are all on the same page on notations and terminology. Okay. And so with these ideas in mind, now we're going to move on to the main topic, which is that of monopole scattering. Okay. And so the motivation is going to be twofold. First, let me tell you a bit about history. So in the 80s, people realized that if you take a proton and you throw it to a monopole, this basically breaks the proton into stuff. So protons decay when in presence of a monopole. And of course, it's a very interesting phenomenological statement, because whatever physics you want to do beyond the standard model that contains monopoles, you have to take into account the fact that the monopoles will make the proton decay. So that's something that puts very, very strong constraints on what we have measured in the lab, okay? But the problem is that when you ask people like, what exactly do they decay into? If you take the technology that was developed in the 80s by Kellan and Rubakov and others, and you put it to the very end and try to find out what exactly goes here, you get very weird answers. So for example, people would say something like, it decays into half a positron plus half a pi, which is a very, very weird statement. Okay, and so this is the first motivation for the study of monopole scattering. I want to understand what people meant by fractional particles, whether that has any meaning at all, or it's just a nonsensical expression. And I also want to explain why they were getting that result. Okay, so the second motivation is like more modern, which is the fact that gauge theories have lots of symmetries, some of which have only been understood very, very recently. So the symmetries of QED are very, very rich. So for example, if you go to the 40s and you ask Feynman and others what are the symmetries of QED, they would have told you that the symmetries are basically SU and F left times SU and F right times U1 axial. So this is rotations of your left moving particles. This is rotations of your right-handed particles, and the axial symmetry, which is just the gamma 5. Okay, but if you go to like a few decades later in the 60s, then Adler, Bell, and Jakib, and other people realized that there were the triangle diagrams that I was describing before, and the conclusion from the 60s, what they concluded is that these triangle diagrams, break this into the diagonal SU and F diagonal, and this one breaks into nothing. So people thought that the symmetries were actually smaller in the 60s. But then if you go to the last decades, in the 14th, Cyber, Willett, and collaborators realized that actually there are more symmetries in QED. So for example,
I don't think they said anything about the SU and Fs being,
no? Okay,
just the U and axial.
okay, well. I mean, it has a mixed anomaly with the gauge group, so they were very bothered by that. A little bothered.
Why does it have
This thing here has an anomaly this time with U1.
nobody looked at that.
Okay, okay. Okay, that's okay.
I think
They
everything,
never, okay,
to my knowledge, not.
okay, cool. Anyway,
Maybe they didn't care because this is unphysical anyway, because an F is 1 in QE.
sure, okay. Anyway, in the 40s, people realized that there were actually more symmetries in QED. For example, there's the U1 magnetic symmetry, which was not something that people realized in the first few days of QED. But then if you go to, for example, 18, Thomas and others realized that this thing is actually not broken, but it's part of a two group with this thing. And it's Q and F, right? It's not broken, even though people didn't think it was broken to begin with. But it's part of a two group with the magnetic symmetry. It's not a direct product. This thing acts non-trivially on this from that factor. And if you go to 22, so last year, Cordova and Shuka and Shah and collaborators argue that this thing here, it's not broken either. The U1 axial is not broken, but it's non-invertible because it has that type of anomaly there. So as you can see, the symmetries of QED have changed over the years, but actually the first answer that people got, it's actually quite close to the correct answer because these symmetries are there. The only difference is that they have some funny features. This one is non-invertible, but it's non-invertible when acting on monopoles. It's still invertible when acting on the fermions. And these two are in a two group with a magnetic symmetry. So we can see that all of these new symmetries are sort of restored, but they still have some funny things, especially when you have monopoles in the mix. Because this thing here measures precisely magnetic charge. This thing here is non-invertible when acting on monopoles. And these two are in a two group with a magnetic symmetry. So again, they behave a little funny when you have monopoles. And so if you were doing regular scattering theory with, where everything is only electrically charged, if you take something like E plus, E minus, annihilating to a photon and E plus, E minus, here everything is electrically charged, you have electron positons and photons, and here all of the symmetries give the regular for the identities. You can pretend that they are regular symmetries. But instead, if you have monopole scattering, so E minus plus a monopole into stuff, here the for the identities are let's say it's not just regular order than the identities because the monopole is explicitly charged under all of these new features. Okay, so the second motivation is that we want to understand what constraints all of these symmetries impose on magnetic scattering. Okay, so these are the two motivations. First, what does this mean? And second, the fact that these symmetries are special, what do they imply for monopole scattering? And it turns out that the two answers are related. And the fact that people in the 80s got like a weird answer was in part because they didn't know about all these new developments. Of course, because they were not known back then. Okay. And so instead of going to the monopole case directly, had lots of different moving parts and stuff. So I'm going to discuss a much simpler toy model. So, which removes many of the complicated features and really goes into the heart of the issue, at least some of the issues, not everything. Okay, so this time model is going to be a 1+1 D free fermion theory. So it's a very, very simple theory. Okay, so free fermions in 2 dimensions, they can be either left-handed or right-handed, like in 4 dimensions. And the equations of motion are very simple. So dt plus dx over left moving fermion is 0. This is the Dirac equation for a left mover. And dt minus dx over right moving is 0. So that means that left moving particles are just a wave that moves at the speed of light to the left, and right moving one is a wave that moves at the speed of light to the right. Okay. And to make this system a little bit more interesting, what we're gonna do is impose a boundary at the origin. That means we're gonna put a boundary here. 0. We have left moving fermions that go to the boundary and right moving fermions that move away from the boundary. Okay. And so the question that we're going to be interested in is what happens if we throw something to the boundary? What comes back? So in general, we're going to have psi left goes to the boundary and it's going to become some excitation of the right moving field. And I'm not going to go into the details, but I'm going to assume that the boundary is as well behaved as it possibly could be. So I'm going to assume that it's conformal, it conserves energy, it's simple, it has finite entropy, blah, 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 whatever qualifiers you can put on the boundary there, okay? And so this thing here, whatever comes out, is going to depend on the choice of boundary condition. So whatever boundary condition you impose on the system is going to tell you what comes out of the scatter. So you take psi left, you bring it to the boundary, use the boundary conditions, and then that becomes some function of psi right, and that's what comes out of the experiment. Okay, so the first naive question that we're going to ask is how is scattering compatible? Oh, sorry, I skipped a step here, which is that the flavor symmetries of the system is very simple. So the flavor symmetry is O to n left times O to n right, where we have independent rotations on left movers and right movers. Okay.
So here you're sure that this boundary condition exists because it's a free theory, right?
Yes.
In general, you have it's non-trivial to show
Yes.
that the boundary that preserves charge or whatever.
I haven't imposed anything on charge conservation yet. I'm only imposing that it's conformal, if you will.
But even here, it's not obviously true.
Yes, no. So to make it conformal, you require that. So if you want just conformal invariance, the only requirement is you have the same number of left movers and right movers. Okay. And so the question that I want to ask is, how is the scattering compatible?
If there was something down, what was it? O2M left?
I'm taking this to be complex. Yeah, so I'm taking NL complex.
Oh, these are bias.
Yes, these are bifermi. The left moving bifermi, right moving bifermi, both complex. So the symmetry is just, you can break it into real and imaginary parts if you want.
Then why isn't it? Oh, okay.
And yeah, sorry, please interrupt me as much as possible. That makes it a little bit more interesting, hopefully. So the question is, how is the scattering of this form compatible with the flavor symmetry of the problem? Because there's something very silly here. This factor here is only charged under the left moving part of the symmetry, and this thing here is only charged on the right moving part. So no expression of this form could possibly preserve both symmetries. This part only carries charge under one subgroup. This part carries charge under the other subgroup. So the whole thing is always broken. So G, F is always broken. And the question is why? Because I haven't said anything about the boundary condition. So I could imagine that some boundary conditions break it, some others preserve it, but the claim here is that every boundary condition is going to break the symmetry. And the answer is simple, because the answer is that GF has an anomaly. If you compute the diagram, so the G diagram in this case, for GF, this is non-zero. And by the criteria that I gave at the beginning of the talk, as soon as you have an anomaly, that implies that every boundary condition is going to break. Boundaries are never compatible with anomalous symmetries. Okay, so this is the reason this flavor symmetry will always be broken by a scattering experiment like this. But there is a more subtle puzzle, which is what makes this model interesting, because now we can look at subgroups of the flavor symmetry. So let's look at the following subgroup, which is going to be a very interesting one. So let's look at U1 subgroup of GL, which is going to be a U1 subgroup such that there is two left movers, psi 3 psi 4, and one right mover, which is psi 5, where these are the charges under the U1. So this one transformed with charge 3 under U1, this one with charge 4 under the U1, and this one charge 5. And I'm choosing these integers because if you now compute the 2-point function of this thing here, it's going to be a sum over all the fermions. The diagrams like this, when you take the fermions here, and then if you put a fermion here and a fermion here, this is going to be the charge squared. So this is proportional to 3 squared from this one, plus 4 squared from this one, minus 5 squared from this one. Minus is because I have the opposite chiralities, and this is 0. So this U1 subgroup is anomaly free. So in principle, there are no obstructions to this symmetry being preserved by the boundary. So this means that there exists some U1 symmetric boundary condition. In fact, this only proves that it could exist. There are no obstructions, but you can actually prove that there is one. You can actually write down a boundary condition that lives invariant these choices of charges. Okay, and the existence of this boundary condition raises a puzzle because now scattering experiments should conserve this symmetry. Okay, so let's say that we begin with psi 3 and you throw it to the boundary, it's going to become some function of psi 5, right? And there are a few constraints. So for example, first of all, okay, let me backtrack a little bit. Okay, so if we throw psi 3 to the boundary, right, to the boundary, well, first of all, something has to return. The boundary cannot absorb the fermion because I'm assuming that the boundary is very nice, it conserves energy, conserves everything. So something has to be reflected back. But at the same time, I'm assuming that the boundary conserves U1 symmetry. So whatever comes out has to be charge 3 object. But it's weird because the only thing that moves to the right in this model has charge 5. So I cannot construct anything with charge 5 with charge 3.
When you give me that diagram there, where the boundary didn't play any role in that. This is the absence of the boundary computing that.
Yes, yeah. So this is basically it's a local computation. I don't care what happens. I can compute this very far away from the boundary. It's a statement about bulk currents. Yeah, it's just a statement about the Toft anomalies. It's a local property.
How do you know that you have a boundary that preserves the U1? Even if it's not anomalous.
Yeah.
Obviously,
So
there is a problem.
Yeah. So there's a sort of like a simple argument and a longer argument. The longer argument is that there's a very, very well developed technology for boundaries in 1+1 dimensions. There's the whole Cardi construction. You can go through that and prove that there is one boundary. So you can
have example for
yes, I have the Cardi state. It turns out that it's unique. So that's a sort of like funny thing that there's only one boundary condition that preserves this U1, and I can write it down. It's like a complicated sum over Ishii-Bashi state, blah, blah, blah. There is perhaps a slightly simpler argument, which is that you can take these fermions and instead of putting them on the half line, you put it on the full plane, but then gauge the symmetry on the half plane. The symmetry is anomaly free, so you can do that. And then by gauge dynamics in 1+1 dimensions, usually when you have like a U1 field with a fermion, you can combine them to a boson. This is what Schwinger did in the Schwinger and Goldman and others, and that is gapped. So that means that you can write down an interface to a gap theory, which is basically a boundary condition. So that's sort of like an indirect argument as to why that symmetry, that boundary condition exists. But anyway, the short answer is that I can actually write it down in the Cardi state. Okay, so here the puzzle is that the charge of any right moving state, this is a free theory, so any state can be written as some action of the right movers on the vacuum, right? So this is proportional to 5, and there's nothing that is equal to 3. So in this theory, there's nothing on the Fock space of the right mover fermions that has the same charge as the ingoing fermion. And that's a very, very weird situation, okay? Hopefully, you're already convinced that this is a weird situation, okay? And so if you go to the 80s and ask Callan and Rubakov and others, what is the outstate in this theory? They would have written something very weird, which is something like this. Psi 3 goes into 3 fields of 5, psi 5. Of course, this conserves charge in a very silly way, but at the same time, it's sort of like a meaningless expression. So this is why people in the 80s were getting like fractional particles. They had many conservation laws, and the only thing that they could write down that preserves the conservation laws was stuff with fractional coefficients. But my claim is that this is not the right answer. This is wrong. or at least very, very misleading. You have to be very charitable with interpretations to claim that this is the right answer. Okay, and so the solution is that the space of local excitations is actually much larger than the Fock space of psi left and psi right. There are many local excitations in this theory that I can construct, but they are not just the action of these fermions on the vacuum. And this is a little bit weird because this is a free theory. There's nothing, I mean, in an interacting theory, I could pretend that maybe there are some instanton effects, blah, 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 but this is a free theory. So this is maybe a little surprising, but when I tell you what these new excitations are, you're gonna see that this is actually something very familiar. So in the string theory or CFT community, these new fields is what people call the twisted sector. Twisted fields. In condensed matter, these are called disorder operators. Okay, and the way they are defined is that these are fields that live at the endpoint of a topological line. So this is a field that is attached to something topological. Another way to say this is that these are fields that are not single value. The correlation function of these fields have branch cuts. Okay, so these are other excitations that exist in the theory. Any theory with topological lines has them. Okay, and the defining property of these things is that they have branch cuts. They are attached to branch cuts. Okay, and concretely, the way you define them in this theory is by taking, let's say, the right mover fermion psi 5, and then if you rotate, you do a rotation around the point it's defined, it is going to pick up a phase. So these are not single value fields, they have branch cut singularities. Okay, and so the twisted sector is defined by whatever phase I choose to put there. And the main point of this construction of twisted fields is that the branch cut adds charges. So the branch cut, this thing here, adds charge. The intuitive way to understand why branch cuts add charge is that if you compute the charge of something with a branch cut, the way you measure charge in general is by surrounding the point by a Gauss sphere and integrating the flux. Okay, so you can write down something like O with a Gauss sphere around it. And this is a charge of the endpoint here, but you're also crossing a branch cut. And when you integrate something and you cross a branch cut, there's an extra contribution from the discontinuity. So that's why adding a branch cut to an operator changes the charge of the operator under various symmetries. Okay, and so there is a claim which I'm not gonna prove here. So the claim is that there is actually unique right moving twist field with charge equals to 3. And concretely it's psi 5 with twist equals 1/5, but it doesn't really matter exactly which phase you put there. There is one choice of phase that gives it charge 3. So that means that the scattering experiment goes something like this. You have the boundary here, you throw in psi 3, it moves to the left, it hits the boundary, and it bounces back, something like this. With psi 5 moving to the right, with a branch cut behind. Okay, so this is the claim for the scattering experiment for this very simple free fermion system. And I want to stress that this is not a conjecture because these are free fermions. Free fermions are CFT, and actually a rational CFT. And for rational CFTs, there's very well developed technology for boundary conditions. One can write down explicitly a boundary condition that preserves this U1 and check that this is literally what happens. As you drag the fermion psi 3 across the boundary, it becomes attached to a branch cut like this. Okay, so this is a rigorous answer. And there are a few conclusions for this simple time model that I want to stress. First of all, if you have an anomalous symmetry, boundaries will always break it. It's impossible to conserve anomalous symmetries by scattering experiments of a boundary. On the other hand, anomaly-free symmetries, they can be preserved. They don't have to be. You can choose boundary conditions that don't preserve it, but you could preserve them if you want to. And if you do choose to preserve them, then scattering experiments must preserve the symmetry. On the other hand, if you have chiral fields, if you have fields that move in different directions, and these carry different quantum numbers under the preserved symmetries, then there's a weird situation where it's hard to write down an out state that has the same charge as the in state. And so typically people will claim that, okay, what comes out is something fractional, but my claim is that it's not fractional. It's integral, there's like a concrete excitation number equal to 1, but it's attached to a topological defect, okay?
You know how to like associate this situation with properties, just the symmetry. Like, so for example, if it has an orthogonal, we say, okay, we don't have symmetry preserving boundary, but here we have something which is completely kosher.
Yeah.
And then we say, for some reason, it's like it's not invertible in nature. But like usually, if something turns out to be non-invertible, we said like, okay, there was an anomaly or something. But here, it's like a priori, it's unclear why.
Yeah, no, I don't think I have a concrete criterion in terms of just the symmetry. I think you have to, I mean, if you have chiral fields and they carry different charges under the symmetry, it's likely that you're going to have this because they're moving different directions and then the outstate is going to carry different quantum numbers. And to make it match, you will have to dress it with a line to make it. But in general, I don't have a good criterion. That's something that sometimes happens. Okay, so let me now move on to the actual problem that we care about. So we're going to do 4-dimensional Dirac fermions. Let's say NF fermions. Okay. And the Dirac fermion has two chiralities, E left and E right. Okay. And under the different groups in the theorem, in U1 electromagnetism, this carries charge, let's say +1 and this one -1. There's also SU NF left. This one transforms in the fundamental, and this one is neutral. That's SU NF right. It's the other way around. And then there's U1 axial, which is the non-invertible symmetry, and both transform with the same sign. Okay. And to this simple theory, we're going to add a monopole, a heavy. In other words, an dot line. And we're going to throw electrons to the monopole and see what comes out. So we're going to take, I don't know, something like psi, either left or right, monopole, and then the monopole is going to stay the same, but the fermion is going to change into some new operator O. And this is the task is finite. We want to know what comes out of the scalar. Okay. And the way we're going to implement the monopole is very simple. We're going to take a very simple description of a monopole. The way we're going to do that is just by writing down the Dirac equation in a monopole background. So we're going to write I del plus A slash psi 0, where A is the usual Dirac singularity. So it's something that has only a component along the angular direction. This is M over R1 minus theta, where M is the monopole charge. Okay. And so we're going to take the gauge field as a background field. I'm not going to have gauge fluctuations. The photon is going to be non-dynamical. But that's fine. You can add fluctuations at the end if you want. It doesn't really change anything I'm going to say because I'm mostly going to discuss kinematics anyway. So dynamics don't matter all that much for this discussion. Okay. And so if you're going to do regular scattering theory, the in state, usually you take it to be a plane wave to the px creation operator AP side. But this is not a very good in state because momentum is not conserved. Momentum is not a good quantum number because the monopole explicitly breaks translation invariance. So you don't want to label states by linear momentum. What you want to label them by is by angular momentum because the monopole preserves rotation. So this is not good. I'm not going to do this. Instead, I'm going to write the in state as in a basis of spherical harmonics instead. Okay. So you put the EDC, energy is conserved, then a spherical harmonic J mu, and then the creation operator E J mu epsilon. So my in state is going to be labeled by its energy, by the total angular momentum J, and by the Z component mu. Okay, and the total angular momentum is basically the orbital angular momentum minus 1/2 from the spin, because it's a spin 1/2 field, and then there is a contribution Qm. This comes from the angular momentum in the electromagnetic field itself. Okay. And the key point, so the key point of monopole scattering is that the mode with L equals 0, so the spherical symmetric mode, the mode without orbital angular momentum. In other words, J equals Qm minus 1 divided by 2. This mode is chiral. And by chiral, what I mean is that dt plus the sign of the charge dr is mode vanishes. So if you take the mode with lowest angular momentum and you take the time derivative plus or minus the radial derivative, where the sign is the charge of the electron, then that thing is going to kill your operator. So that means that that perturbation only moves in if Q is positive. That moves in, and if Q is negative, it moves out. So the mode with lowest angular momentum either only moves inwards if you look at the left moving electron, and it only moves outwards if you're looking at the right moving electron. Okay. And so this is basically the same situation we had in the toy model from before, because before we also had things that only move to the left or only move to the right, but they carry different charges under the different symmetries. Okay, and in this situation, the monopole basically behaves like the boundary before. Okay.
Just to be clear, for higher L, this chirality will not proceed.
The thing doesn't vanish for the higher ones. So the higher angular momentum modes, they can move either in or out. They're both valid directions of motion.
Here's a small question. You're assuming here that everything is mathless, right?
Yes, sorry.
If you add a small math, then everything is broken to the vector-like subgroup, and there's no problem.
So if you add the mass, this is broken into the diagonal, this one is completely broken, the axis is completely broken, and these modes are not chiral anymore. They basically, yeah.
And then there's also no puzzle.
There's no puzzle, yeah, correct. Although there is a partial puzzle in that case, because when you're very, very close to the monopole within the Compton wavelength of the electron, you can sort of pretend that it's massless anyway. So very, very close to the monopole, like the first few milliseconds after the scattering, you can pretend that these symmetries are restored. The component that moves to the left inwards is going to be like the biggest partial wave. The one that moves out is going to be very, very suppressed. So there is sort of like a small version of the puzzle that only exists very, very close to the monopole. And eventually, well, yeah, I might say something about that later.
Here the puzzle only exists for the S wave? Or
yes, for the S wave.
For the other ones, I mean.
No, yeah, because the other ones can move in either direction.
Yeah.
So you throw something in.
So it means so it is.
Yes, correct. Okay. Okay. So the first question that we're gonna ask, which is a very simple one, is that what happens to SU and F left times SU and F right? And you can see that the E left, this one goes in, E right goes out, and this one has charge, it's in the fundamental, but it's neutral under this one and the other way around for the other one. So if you throw E left in, and it's gonna come out some function of E right, this already breaks the symmetry. Okay, so it's impossible to write down something that has the same charge as the in state. And the answer in this case is very simple, because SU and F left times SU and F right is in a two group. So that means that the monopole explicitly breaks the symmetry. This symmetry is not conserved in monopole scattering. The monopole is explicitly breaking the symmetry. So this is why you may sometimes say that symmetries that are in a two group, they're sometimes conserved, sometimes they are not conserved. When you do scattering without magnetically charged stuff, it is conserved and mostly behaves like a regular symmetry. But if you do scattering with magnetic stuff, it's broken. You should forget that the symmetry is there to begin with. It's explicitly broken. There's question two, more subtle version of the symmetry of the question, which is that now SU and F vector. That one is not part of the two groups, so that one should be conserved. Okay, so this one should be conserved. But there's still something weird, because if you look at the diagonal here, they both transform in the fundamental, but if you look at U1 electromagnetism and the U1 axiom, this one transforms with +1 -1, and this one with +1 +1. So even then, it seems impossible to conserve everything at the same time. Because if you write here something like, you write this thing here does preserve this one, it preserves this one, but it breaks this one. And if you try to put like a dagger here, now this one is conserved, but these are broken, and you can convince yourself that it's impossible to write anything here that has the same quantum numbers for everything. So now we have a more subtle puzzle because we have a symmetry that should be conserved, it's not part of the two group, but at the same time I cannot write anything that is consistent. And the answer of this more subtle problem is that the outstate is accuracy. It's exactly the same situation as before. You have things that move in different directions, they carry different quantum numbers, and the only way to write something that has the same quantum numbers that moves in the right direction, but has the same quantum numbers as whatever came in, is by adding a branch cut. Okay? So the claim in this case is going to be something like this. So you take the S wave, the spherically symmetric radiation, with the monopole here goes in, and you put here the S wave of the left moving electron, and this is going to become something like this. It's going to move out. It's going to be the S wave of the right moving one with the monopole here, but there's going to be a three-dimensional branch cut here. Okay, it's much harder to draw. I don't know how to draw a three-dimensional branch cut in 4 dimensions, but you have to imagine that it's more or less the same as before. As the wave moves out, it leaves behind like a three-dimensional branch cut. Okay, and when you go around the branch cut in 4 dimensions, you pick up a phase. Phase. You actually write it down. It's E left. It's e to the 2 pi I over m f. E left, and E right. It's the same phase, e to the 2 pi I over m n f. E right. So this is just a U1 axial rotation by angle. M is the magnetic charge on the monopole, and Nf is the number of fermions. So we're putting here inside a defect for the axial transformation. Okay, and in general, as I mentioned at the beginning of the talk, the defect for the axial transformation actually carries a 3-dimensional TQFT, and it's a non-invertible thing. So this branch out here is also stacked with a 3-dimensional topological theory, which adds some ingredients that I'm not going to get into because it would take too much time. Okay. So this is where my notes end. Let me check real quick if I'm forgetting anything super important. If there are any questions, meanwhile, I'll be happy to. Oh, okay. This space here that I'm writing here, there are different ways to compute it. One of them is by looking at the anyons of the 3-dimensional TQFT. You can do some computations, because if you remember that the top line basically transform it's addressed by a Wilson line under an axial transformation, and this one carries electric charge +1, this one carries electric charge -1. So you want the defect to add 2 units of electric charge. So you want here the Wilson line of charge 2, and you can compute the anyons here, and you can see that with this specific choice of phase, this Wilson line requires 2 units of electric charge. So it adds whatever you are missing. There is an independent argument, which is that everything here is spherically symmetric. So you can do dimensional reduction along the angular directions, and you end up with a 2-dimensional model. Is the electrons only depend on time and the radius. Okay, so it's literally identical to the 2-dimensional model from before, and you can again compute the discontinuity across the branch cut in the 2-dimensional model, and you get the exact same answer here. Okay, so there are different ways of computing whatever comes out here, and they are all give the same answer. Okay, and so what is the sort of take-home message here? First is that if you want to do monopole scattering, you need the full machinery of generalized symmetries, because if you didn't know the fact that 2 groups are broken by the monopoles, and the fact that the axial symmetry is not broken, but it's non-invertible, you will never find a consistent answer because it's not possible to write down something that is consistent without this sort of structure, okay? And the fact that it's non-invertible is important because you need the Wilson line here. There are lots of ingredients where the full machinery of generalized symmetries really makes a difference. But it's sort of like a weird situation, right? Because here we have a scattering that turns like a regular stuff into a twisted thing. I'm not sure how to measure that in the lab. It's not as problematic as it may seem because twisted things are locally, they're indistinguishable from untwisted things. The only difference is global. It means that when you go around it, you pick up a phase. But any local measurement is not going to detect a branch cut of that form. So it's weird that the S matrix takes you to a different sector of the theory, but still, phenomenologically, it will be very hard to see that. It will behave for the most part like a regular particle. You will not measure something super weird in the lab, okay?
So does it go around and you go around?
In 4 dimensions, I don't know how to draw it.
Not around the outgoing particle, but you have to go around the entire.
Yes.
What exactly do I do to measure it?
So let me draw it in 2+1 instead of 3+1. Maybe it's a little bit better. So let's say this is time. This is
supposed to like live on the light comes. Okay.
so in this case it's a 2-dimensional disk instead of a 3-dimensional. So here is a 3-dimensional ball. In 2+1 is a 2-dimensional ball. So what I mean is that you go around it in the time direction. So you go up in time and you cross it spatially. It's a little bit difficult to draw. So this is in 2+1. And that makes it a little bit better. It's in space. I mean, it's not in space. In space, it's a ball. So you have to go around it in the 4th direction. Yeah, I'm not very good at drawing. In 1+1, it's perhaps even better because here you have, this is time, this is space, and now it's a line instead. And by around I literally mean like this. This is in 1+1, this is in 2+1, in 3+1, I don't know how to draw.
But in the 1+1 case, I mean the twisted sector, I mean here it's a local operator at the end of the line.
Yes.
Corresponds to some state in the twisted equals.
Yes.
Fine. But in 4D, it's like the operator at the boundary is.
It's a 2-dimensional thing, yes.
Yeah.
So it's describing
So it's like
spherically symmetric radiation. It's not a state, it's a 2-dimensional, yeah. I'm not sure what the best terminology is.
Yeah, it's like the operators, yeah. So it's like loop excitation, so
Something like that, yeah.
It's worse.
I don't know what the best way to say it is. Let's see if there's anything else. Okay, so maybe going back to Thomas' comment from before, if there is a mass, the mass explicitly breaks the axial symmetry, so that means that this defect acquires a finite tension. So when you're very, very close to the monopole, this picture still holds because you can pretend that it's massless, but as it grows out, the tension eventually will make it break. So eventually, if you have a finite mass, this thing here is going to be true for the first few milliseconds of the scattering, but eventually it's going to break, the defect is going to snap, and you're going to get an untwisted thing. So if you keep waiting long enough, you're going to get like a big untwisted thing without any defect. Okay, this is for the massive case. And I think that's all I have. So thank you very much for your attention.
Yeah, and follow up to that. So imagine that we're doing this some ESM setup that's a grand unified theory and it has monopole. Then all of these symmetries are also emergent, right? Both the U1 magnetic
Yes. Yeah.
is not actually a microscopic symmetry, and the U1 axial is also not. If you UV complete this.
Yeah.
So the exact without adding the electron mass by hand, if you don't want to. So they will somehow something similar should happen. Eventually, this thing will snap, and
Well, it depends on which specific choice of UV completion you're having in mind. Because if let's say I have, so here I'm taking the monopole to have some generic magnetic charge M, right? And you can write down a UV completion where that monopole is still non-dynamical. It would just mean that the UV completion has a ZM quantum symmetry. So in our case, it's a U1 magnetic symmetry, but the UV completion doesn't have to break it completely. You can break it something like this. And in that case, you don't need to talk about, like, the monopole could still be just would be in a tough line for this thing. and it will have infinite mass, so you don't need to talk about substructure. And the other symmetries don't have to be completely broken either. So for example, the U1 axial, in this case, doesn't have to be completely broken, it could be broken into ZM, zero form symmetry. So many of these symmetries could survive depending on which specific choice of UV completion you have in mind. If you have a UV completion where the magnetic symmetry is not completely broken, but there is still like a
This is a fun theory exercise, but if you're interested in actual,
yes.
presumably actual gut
Yeah.
monopoles, this is exactly what it doesn't have.
No, exactly, yeah, no. So if you do the full standard model, that's part of the work in progress with Rishi. There's a very similar story. Now the symmetries is just the standard model symmetries, is U2 times U1. And there's what, U1 B minus L, depending on what exactly if you choose. I mean, let's pretend that there are no Higgs, so the U couples are zero, everything is massless. Okay, so these are the symmetries that you have to conserve. And then you can choose some monopole in some U1 subgroup here. Depending on which U1 you choose, there's going to be some spectrum of in-moving excitation, some spectrum of outgoing excitation, and you can run the same exercise here. And what we find, well, it's not clear what we find yet, but we find that for some choices of monopole here, you still need a defect like that. Although it's going to be a much simpler defect, it's going to be just a sign here. It's going to be like a minus sign here. So it's a much simpler.
-1 to the F.
It's like a -1 in B minus L sort of. I don't think it's exactly -1 to the F. I think it's no, wait, sorry, I'm saying I'm going to have something wrong. It's a -1, but it's sort of like inside this whole thing. It's a -1 that acts non-trivial in every sector here. It doesn't act like a -1 on every fermion in the system, only on the ones that have non-trivial chiral states. Not every fermion gives you a chiral operator. The spherically symmetric mode depends on the charges of the individual fermions in the theory. And the fermions have different U1 charges and the different U1 subgroups here. But not every fermion gives you something that participates in the scattering. There are many fermions that are completely transparent to the monopole. So there's a minus sign that acts on the fermions that do participate in the scattering, but not as a minus sign on the other. So it's not just -1 to the F. But there are many weird features of the full standard model we don't understand. There seems to be some sort of like open questions that we don't have a good answer for.
But in these cases, what you say is pick your one U1, okay, that's. Is every single one of these cases UV completable to a situation where this U1 monopole is dynamical, or do some of them have to be defects? So in other words, is there ever a situation where there's a gut and you have a dynamical, nice, smooth topological monopole and it has something like this or not?
I think so, yeah. I think even for the in QED, you can complete it into an IC2, right?
No, but that explicitly breaks both the U1 magnetic and the U1 axial. So all the symmetries that you care about are out the window. That was the origin of my question.
Yeah. Okay.
So the question is if this persists, like
Yeah, is there ever a UV completion where this where this is inevitable for dynamical monopole scattering?
Yeah, I'm not sure.
What sets the scale at which the sheet breaks?
The sheet breaks when you have a positive mass. So it's like 1/n, basically. When you have a non-zero mass. If you're doing QED with strictly massless stuff, is one that never breaks. It has.
So let's say we take your SU2 completion.
Yeah, that and
then with zero mass.
I would assume it's the scale at which the non-abelian degrees of freedom.
But there are two scales. One at which the U1 magnetic is broken, which is the monopole mass, and one at which the U1 axial is broken, where the chiral symmetries are broken, and that's more like the W boson mass or something.
I would say that it's the axial one, because that's the one that is like setting the tension here. But I'm not sure.
No, it's not, that's not quite true, because in order to make this sheet topological, you also need to use the one form symmetry, because you need to stack it. So I think both,
Yeah.
I think both are relevant.
Well, okay, there's a non-trivial fact here that I was skipping, which is that, okay, let me. So in the QED example that I wrote down here, it's an axial transformation with this specific phase, right? So you don't need the full U1 axial, you only need the Z,
Oh, I see.
M, NF subgroup. And that one doesn't need the one form symmetry.
At all?
No, this one is not part of
Oh,
the
that's
two.
true. This is the non-anomalous.
Yes,
So this is actually a conserved,
yes, this one is exactly conserved, it's not part of two group, yes,
and it's invertible.
yes. Well, I don't know, it acts like this on the fermions. I think it still acts on the monopoles, but it acts on the monopoles, but attaching an integrally quantized Wilson line, not fractional. So I think it's invertible also on the monopoles, yes,
Invertible.
yes,
This is what in the old days you would have called the non-anomalous subgroup.
yes.
Okay, good.
So I think that the surface that you attach is this one is
Yes.
invertible. So
Okay.
No, it's this is still non-invertible, yes. The invertible subgroup is ZNF. This one is
Oh,
invertible.
sorry, when M is not one, that's fair.
So this is still non-invertible, I would say, yes. It's sort of for a minimally charged monopole, only the invertible part matters. It's only for the higher charged monopole that you do need the non-invertible thing.
So it's the scale of the U1 axial breaking.
I think so, yes.
at the level of operators, like say what is attached to it. It's like you integrate a fermion on this sphere, and then it is attached after it's scattering to.
Yes. So you have the fermion integrated on the sphere, and in the interior of the sphere, you have the ticket inside. Yes.
This is okay because I mean we're only restricting anyway to the S wave, right? So
The higher order modes, they are not chiral, they move in both directions. And so you don't need to attach anything. The conservation is very simple. You just send in the in-moving mode, and the outgoing mode comes out just with some phase shift, but it's still everything untwisted. You don't at that point. Because the in mode and outgoing.
is there something special about m equals to 1 in the units, the charge monopole? Because it's invertible versus not.
Yes. No, the only difference.
Fermion, I mean, do you see like the fractional fermion, something?
No, let me think. I think people, if you will go to the 80s and do what they would write, I think
Like all the puzzle, like the curve overclock and everything is the same. The unit.
for m equals 1, you still have some, it's still the same puzzle.
Yeah.
People would have written something like psi goes to something like 1 over nf psi, something like that. It's still maybe with a suki. But it's still fractional, yes, it's still the same puzzle. Yeah.
You don't see anything qualitatively different between them.
No, only that it's invertible. Yeah. So even for the minimally charged monopole, you still have the same puzzle.
But now I'm confused because if we take M equal to 1, and let's take also NF equal to 1.
Okay.
Like let's take honest to God QED with a minimal charge moment.
Yes.
Then you're saying that alpha is 1. So you don't need any surface.
No, exactly. Yes. For m equals 1 and nf equals 1, I can write down an outstate that has, I can do just E left goes to E right dagger. There's no SUNF symmetry. This is not valid in general because there's
of SUNF. See, this preserves both U1s, but
only the U1 is the only symmetry that you have here.
the charge and axion.
Well, there's no axial here, right? It's okay. Yes. The thing is that you only need to conserve this group of the axial symmetry. You don't need to conserve the full axial symmetry because the full axial symmetry is part of the two groups. So it's also broken by the monopole. So in general, the symmetry that you have to preserve, so in general, you have to preserve U1 electromagnetism, that's U NF vector, and Z M NF. You don't preserve the full axial, you only preserve this. Because, well, left and right are separated into two groups, so it's broken only to the vector one, and U1 axial is also part of the group. This is the subgroup that is not part of the two group. So this is really what you should preserve in general, not U1 axiom. I wasn't writing U1 axiom to simplify it.
I understand better the assumption that led to this. So you're assuming that the boundary condition on scoring the monopole is simple.
Yes.
So it doesn't have any labels
No.
that could transform under
Mhm.
the things that are in the two group.
Yeah.
Is it logically possible that this happens in some examples? That you have non-simple?
Something that is in a two group will never be preserved by the boundary, whatever you choose.
I know, but the boundary could have a label and transform into a different boundary.
Oh, right. So the boundary is it absorbs charge basically. Yes. So in that case, there's no puzzle because you can throw in something and the monopole absorbs whatever you threw in, and that's fine. There's no puzzle there. Nothing has to come out if you have.
Well, I'm asking, does this happen in any that models, or is that not a valid option?
Yeah, I think if you go to so a UV completion of QED can only preserve this at most. It cannot preserve anything more than the U1 vector, right? Because left and right separately are in two group. But it doesn't have to preserve this. It could preserve something smaller.
That's right.
So if you choose that UV completion, then yeah, that's what happens. Basically, only what the UV completion preserves, the monopole preserves. Yeah. Basically, the two group is telling you what the boundary condition is preserving to the image.
I wonder whether like you can test the uninvertibility of the different distinguished between equals to 1 and 2 by either scattering with another monopole or just scattering the extended the twisted.
Yeah.
That's what to believe.
No, it's a good question. We try to answer that type of questions. We have no idea. We don't even know exactly what defect goes here. We know that it's a defect that has to implement this phase, so it has to be stuck with some TQFT, but we don't even know exactly which TQFT goes here. The whole state is the minimal TQFT that does the trick, but it could be some other TQFT here that doesn't couple to anything. Well, it doesn't couple to the one form symmetry, it will. It might couple to something that we don't have enough.
It may not be universal.
No, exactly. Well, if you want to fix the U1 axial into something that is symmetry, there's no universal answer. But if you choose QED with a concrete choice of UV completion, that should give you a complete
No, of
answer.
course, it's true.
Yes.
But in the UV completion.
Yes. So the UV
No,
completion
actually-
should tell you what TQFT
So
goes
you
here.
cannot solve this in
No, exactly. Well, we don't know if there's anything more sophisticated that you could do that could tell you something about the TQFT, might tell you how many vacua there are. We don't know. We don't think there's something that is going to fix it completely. There might be further constraints that gives you some more information about the TQFT. We don't really know.